start. Okay, so let us get started. So we start to discuss Lorentz invariant quantum field theory last week, and I try to quickly review relativity. And for some of you who have not been exposed to this kind of tensor notation, I hope that the current homework problem would help you to get this idea. And the whole point of using this kind of notation is basically make the whole relativity just mechanical thing. You don't need to think. You just make sure that you use these the indices, and always the contract indices between upper index and lower index. And difference between upper and lower index is that the sign of the spatial components have been reversed. And that way you can build these Lorentz invariant combinations without basically thinking about it. So that is the sort of the purpose of using this kind of notation. And the 4 momentum vector is an example of such a 4 vector with the upper index, and you combine energy and momenta into the single object, and they transform as this 4 vector under the Lorentz transformation. And to make sure that every component has the same unit, you use speed of light. So energy mod speed of light is the component, time component of this 4 momentum vector. And switching to lower index, you reverse the signs of the spatial components. Then if you multiply them together in sum of the repeated indices, you find this combination of E squared over C squared minus P squared. And this combination indeed is Lorentz invariant, namely just a constant given by the mass of the particle m squared C squared. So this is an example that once you have some combination which is known to behave as a 4 vector, then it's easy to build an invariant which is not does not depend on the reference frame. So even when particle is moving or at rest, this combination is always the same given by the mass of the particle. So when the particle is at rest, momentum vanishes, E energy is mc squared, that gives you m squared c squared. When the particle is moving, the energy has 2 components, the rest energy of mc squared and kinetic energy. So the total energy turns out to be given by this combination, p squared c squared, so m squared c to the 4th. And as we know that if you go to non-relativist limit, where momentum is less than mc, you can do the Taylor series expansion in p, and you see the familiar expression for the kinetic energy for a non-relativistic particle. But for an arbitrary momentum, which may approach mc or even go beyond that, this formula is always true. And that's because this combination is fixed by m squared c squared. Just by moving p squared to the other side of the equation and taking square root, you find this expression. So once again, you don't need to remember this kind of formula anymore. The only thing you need to know is that energy and momentum combine to this 4 vector. Then you immediately know that this combination is Lorentz invariant. And that's given by the mass. And then by solving this backwards for the energy, you can now derive this expression for the relativistic energy of a point particle. And so this is already being used for. So you don't, as I said, you don't want to memorize stuff in physics. You can derive everything from the first principle. The first principle here is the fact that energy and momentum transform as a Lorentz 4 vector. And that's pretty much all you need to remember. And then you can derive this expression for energy right from there. And for the massless particle like photon, you set m equals 0 in this formula, then you do arrive at this expression E equal PC. That's something we have been using all along in dealing with the quantized Maxwell field. And we also can immediately see that this plane wave factor has the meaning of Lorentz invariant expression, because the p dot x in the exponent, where p is a 4 vector, and x is also 4 vector ct x y z. And then this dot is meant to be this contraction of indices between lower index and upper index. Then you immediately can write down this as et minus p dot x. And this is the form we have used again all along, without knowing that this expression is relativistic. But it turns out to be the right combination we have used for any waves we have encountered so far. And so now we know the origin of this combination ET minus PX. This is meant to be Lorentz invariant, and we may not be aware of the fact that we have been secretly using relativity behind this wave factor, but we have been, because nature knew better than us that nature has to be Lorentz invariant. Maybe we didn't, but because nature told us that the wave goes like ET minus PX, and in retrospect, we say, aha, this actually came from relativity. And nature was smarter than us, so she already told us that this is the right wave factor to use. So in that way, we can use this Lorentz invariance very easily to come up with the expression which has the Lorentz invariant meaning. And the only thing you need to know is that energy combines with the momentum and time combines with space. And that's pretty much all you need to remember. Then everything follows from that. So that's the discussion I had last week. And then we extended this discussion to derivative. The only tricky thing you need to know is that when you take derivative with respect to this 4-vector x mu, ct, x, y, z, because you're putting this upper index downstairs, the whole object ends up having a lower index. So that's a little tricky thing you need to really know. So when you define the derivative, you define this derivative with respect to ct, x, y, and z. So altogether, they form this 4-vector, 1 over c dt, dx, dy, dz. But this 4-vector behaves as a vector with a lower index instead. So that's the important thing you need to know. And the quick check I mentioned to you, why regarding this to be lower index makes sense, is that if you compute this combination and contract these indices, del mu x mu, then derivative acting on x0, that's ct, is 1. Del x acting on x is also 1, 1, 1. So you sum them up, that gives you 4. That's space-time dimensions. That certainly has a Lorentz invariant meaning here. But if you hadn't appreciated the fact that this is a lower index, then you would make a mistake on the sign of the spatial components. So instead of 4, you end up getting -2, which is a nonsensical result, has nothing to do with the 4-dimensional space-time. So that's how you know that you made a mistake there. So you really do need to regard this 4 derivative to be a lower index vector. And once you know that this derivative behaves as a 4-vector, then you can immediately build the Lorentz invariant again. So G mu nu flips the sign of the spatial components and sum over the indices. So you find this combination to be given by 1 over c squared del t squared minus Laplacian over the space. And so this whole combination, again, is meant to be Lorentz invariant in called the Lambertian. And instead of using this triangle for the Laplacian, which has 3 vertices, which represent the 3 dimensions of space, now we are dealing with also time. So that's why we use this square symbol, representing 4 dimensions for each of the vertices. That's the idea of this notation. And so this Lambertian then is a Lorentz invariant derivative operator, which we can use for the wave equation. And we'll get to it right away, called the Klein-Gordon equation, in a couple of slides. And here again, we just make sure that this derivative vector is actually a lower index vector. So by acting this derivative operator on this wave factor we talked about, which has the Lorentz invariant meaning, it is supposed to extract momentum with a lower index. So indices have to be consistent on both sides of the equation. In fact, when you take time derivative, you do extract E, that's the energy, from e to the minus I et over h bar. So that makes sense. But when you take the spatial component, because of this minus sign in dot, that gives you the opposite sign, namely minus momentum. And this is something we knew also from quantum mechanics class, because in order to represent momentum with the derivative operator, you don't write IH bar, you write H bar over I, right? So that's how momentum operator is represented in position space. So you are actually switching the sign from time component IH bar del T to the spatial component H bar over I del I. And that change from I to minus I, or I to inverse I, comes from the fact that this is actually a lower index vector, which has the opposite sign for the time component, that is the energy, versus spatial component, that is now negative momentum. So once again, in quantum mechanics, we already knew this, that you're supposed to use IH bar del T for the Hamiltonian or energy, H bar over I gradient for the momentum, without knowing why time and the space are treated differently by a sign. But now you see the origin of this, that the difference in sign between Hamiltonian and momentum, when you write this in position space, is due to this negative sign that appears between the lower index vector and the upper index vector. That's where it came from. So this is another example that we didn't know that this actually came from the relativity, but nature knew that because she knew that her space-time is relativistic and Lorentz invariant. So she gave us this position representation of the Hamiltonian and the momentum, and there was already a sign in there. But now we do appreciate that this sign difference between time and space, when you write momentum and Hamiltonian, originates from this minus sign that appears in this the lower index vector in the Lorentz transformation. And finally, now that we identified this H bar times derivative with the 4 momentum with the lower index, you put them together again between lower and upper index to build the Lorentz invariant, then acting this minus H bar squared D'Alembert that would extract m squared c squared. So this is the beginning of the seeing relativistic wave equation, which turns into what is called the Klein-Gordon equation. So using this Lorentz invariant notation, which is just mechanically adding up the indices between lower index and upper index, you can start building these Lorentz invariant operators, and immediately you find this a candidate wave equation to describe relativistic particle, namely Klein-Gordon equation. So that's what we discussed so far last week. And let me stop here. Are there any questions about what we discussed so far? Don't be shy.
Okay, Professor, this is kind of silly, but is there any significance to the box there on the last bullet point?
Yeah. So this box represents 4-dimensional space-time. It has 4 vertices. So it is meant to give you 4-dimensional derivative operator. On the other hand, when you write the Laplacian, you use this triangle, right? That's the common notation for Laplacian, which represents 3-dimensional space. So this is the Laplacian given by gradient dot gradient, and that has the 3 derivatives as part of it. That's why we use this triangle to represent 3 dimensions. But now that we also include time, and this is fully Lorentz invariant derivative operator in 4-dimensional space-time, we use square instead.
I see. Thank you.
So that's, in some sense, a little joke, I guess, or sense of humor by mathematicians. And they do a lot of these things, right? But I have never seen pentagon being used for 5-dimensional derivatives. So I don't know how universal this idea is. Any other questions? Thank you, Mashit. I see chat. That's cool. I've never seen the symbol used before. Okay, now you see it. So this is a 4-dimensional space-time. Any further questions at this point? Okay, so this is basically all about notation, but I hope you are seeing that this kind of notation is useful because you don't have to stop and think each time how to write down Lorentz invariant objects. Just mechanically adding lower and the upper indices, you automatically get these Lorentz invariant objects, and that's why it is so useful. So one thing you do need to know is the Lorentz transformation. Again, we talked about this last week, but let me go through this once again because that's part of your homework problem now. So I already told you that this Lorentz invariant inner product between 2 Lorentz 4 vectors, A dot B, is given by this metric tensor G, so that I add time component with a plus sign and spatial components with minus signs. So this is A naught B naught minus AXBX minus AYBY minus AZBZ, and that's the meaning of this A dot B. So I can write this using this matrix notation. B is a column vector. This G matrix is sandwiched in between, and A transpose is a row vector. If you multiply them together, then you recover this A dot B. But the advantage of using this matrix notation here is that when you think about Lorentz transformation, that's a linear transformation on the vector. So L is a 4x4 matrix acting on this column vector B. Maybe I should actually use the laser pointer to make it a little bit more visible. Annotate, spotlight. Okay. So now I think you can see this better. And let me go back. So when L 4x4 matrix, which ends up of this form, given by these parameters called gamma and beta, this 4x4 vector represents the Lorentz transformation L, acting on 4 vector B. And same here, same Lorentz transformation L acts on 4 vector A, which is transposed as before. And so what we want to make sure is that this A dot B doesn't change before and after the Lorentz transformation. So that immediately tells us that the condition for this being invariant translates to this condition on the matrix L, such that L transpose GL is the same as G. And this condition looks familiar when G is just a spatial component 1, 1, 1, because this is nothing but the condition for the orthogonal matrices for spatial rotation. So when you have 3x3 orthogonal matrix O, O transpose O is identity matrix. That's the condition for the rotational matrices. So this is just a generalization of this, now including the time component. So if you specialize this condition just for the lower 3x3 components, this is nothing but the ordinary spatial rotation given by orthogonal matrices. So the only new thing we have to think about is the linear transformation that involves time. And that corresponds to the Lorentz boost along X direction, Y direction, or Z direction. So in general, Lorentz transformation consists of 6 types of operation. You have spatial rotations around X-axis, Y-axis, and Z-axis. So you have 3 independent rotations. Then you have 3 independent Lorentz boosts along the X direction, along the Y direction, and along the Z direction. So you have 6 operations altogether as a part of the general Lorentz transformations. And now we try to come up with an explicit form of the matrix by specializing to this X direction of the Lorentz boost. So Y and Z part doesn't do anything. So I'm only looking at this upper 2x2 block, which has to do with time component and the X component. And here what I'm verifying is that if I use this matrix gamma, gamma beta, gamma beta, gamma, and sandwich this 1 minus 1 part of this metric tensor G between these 2 matrices, you can immediately see that off-diagonal components vanish, which is a good sign. But in addition, I have to make sure that this combination gamma squared 1 minus beta squared has to be 1, so that this LGL is G, going back to the original G with 1 up here. And once you satisfy that, the second element, minus gamma squared 1 minus beta squared, is automatically minus 1, so I don't get a new condition. So all I have to make sure is that this combination, gamma squared 1 minus beta squared, is 1. So I can solve for gamma then, as a function of beta, that gamma is not independent from beta, but just given by this 1 over 1 minus beta squared square root. And this is the kind of expression you have seen probably in the freshman physics discussion on modern physics of the special relativity, where beta corresponds to velocity over speed of light, v over c. That's a common notation for v over c, which is always called beta. And this combination is always called gamma. I don't know historical reason for this. Some people told me that maybe that's because people used alpha for the fine structure constant, and then the next 2 letters turned out to be beta and gamma. I don't know if that is the right story, but that's at least one way you can remember these things. So this is the general expression for the Lorentz boost. And what I'm asking you to do in the case of the homework problem is by expanding this gamma beta matrix to the first order in V, you can derive that this Lorentz boost now reduces to Galilean boost to go from one reference frame in Newtonian mechanics to another reference frame that's moving relative to the original frame to the linear order in V. It really does reproduce the Galilean boost. So the Lorentz transformation is more general than Galilean boost because you can go to a much higher speed because it includes all the orders in power expansion of V over C. But that way you can make sure at the relatively low velocity, it matches up our intuition based on Newtonian mechanics. And that's one thing you are going to check in the homework problem. So as a result, so this is the general expression for the Lorentz boost. You can go from any reference frame to another reference frame. And this is, again, not something you need to remember because we derived it from the requirement of the Lorentz invariance. And requirement of Lorentz invariance is that this metric tensor G doesn't change under the Lorentz transformation. That's this condition, L transpose G, L is G. And once you know this condition, you can derive that the Lorentz transformation has to look like this with the gamma and beta given by this relationship. So again, you can derive everything from the first principle of the Lorentz invariance. Okay, any questions about this? Okay. And then we already applied this Lorentz transformation for a useful purpose, namely that when you have the full momentum vector in rest frame of the particle, energy is just the rest energy mc squared. The time component of the full momentum vector is energy over c. So the time component is mc as a result. And it's at rest, so there's no spatial momentum. So this is the momentum 4 vector, energy momentum 4 vector in the rest frame of the particle. Then I can immediately apply what we derived on the previous slide to go from the rest frame to a moving frame using this boost matrix. Then you can find that 4 vector now looks like this. So energy is now changed from mc to gamma mc. And now you have the spatial momentum gamma mc beta. So by explicitly writing it down using the velocity, you find that the energy, which is the time component times c, is mc squared times gamma. We derive the gamma is 1 over square root 1 minus beta squared. And that is probably the expression you have seen before in freshman physics class. This is the energy of the relativistic particle moving at speed v. And correspondingly, momentum is given by mc beta gamma. And c beta is v. So you have mv upstairs. And this is the case when the momentum is in x direction. If it is moving in general direction, this v, of course, becomes a v vector instead. So what you have upstairs is mv. And I have a factor of gamma that gives you this square root 1 minus beta squared downstairs. And once again, when velocity is small, you can ignore beta squared downstairs and the momentum reduces to the familiar expression of mv, which we learned in Newtonian mechanics. So for low velocities, everything reduces back to the Newtonian mechanics. But now this is fully generalized to arbitrary velocity, which may even approach close to the speed of light, like protons in LHC, and you can obtain the momentum for that kind of high velocity. So again, this is not something you need to remember. We just derived everything from the first principle just by knowing that energy and momentum together behaves like a 4 vector under the Lorentz transformation. We could go from the rest frame to moving frame, and there come out the expressions for the energy and momentum in this moving frame for a point particle of mass m. So everything is derived from the first principle of the Lorentz invariance. And in the last part of the homework problem, I asked you to derive the speed of the proton in the ring of Large Hadron Collider, which has the energy here of 7 giga electron volt. I've given you the mass of the proton 0.938 giga-electron volt in the same unit. MC squared is given in that unit. And then knowing MC squared, knowing E, you can work out beta. Knowing C, you can work out V. So you can then work out to what percentage of speed of light proton has achieved in the LHC tunnel, which is something like 99.999% or something. So you can exactly work that out using this expression. So that's what I'm asking you to do. So just familiarize yourself to the special relativity and get some insight into intuition behind these formulae. Okay, any questions about this? Everything okay? Yeah, this is probably review for many of you, so I'm not surprised. But again, there's no stupid questions. No questions are stupid, and don't be shy to ask any further questions if you have any. Here's the chat. Oh, good. It's nice to see something familiar. Okay, I'm glad to hear that. All right. So now we come back to the Maxwell equations, and historically, the Lorentz invariance was discovered as a symmetry of the Maxwell equations. But we are now doing it backwards. Now we know the Lorentz invariance is a true symmetry of the nature of a space-time. And then we would like to promote Maxwell's equations to a fully Lorentz invariant fashion, which turns out to be a lot simpler than this set of Maxwell's equations. So the idea is, again, put together everything in terms of the 4-vector under Lorentz transformation. So to write down Maxwell's equation, we have the scalar potential and vector potential, and they actually combine together into a 4-vector, a mu. Mu, again, is this upper Lorentz index. And to make sure, again, that everything comes with the same unit, scalar potential over C and vector potential have the same unit, it turns out. So you combine them together to build a 4-vector, a mu. And you also combine the sources into a 4-vector. This is the charge density rho and the current density J. And it turns out that charge density times C has the same unit as the current density J. So rho C and J together form a current 4-vector, again with the upper index mu. So these are the building blocks to write down theory for electromagnetism. And the field strength, E and B, is combined into this 6 tensor. So mu and nu indices both take values from 0, 1, 2, and 3. So I have 4 possibilities for mu, 4 possibilities for nu. But F mu nu is basically a curl, just like the magnetic field is when you write it in terms of the vector potential. But this is the 4 curl instead of 3 curl. So mu and nu indices take values from 0 to 3. But because it's a curl, this is antisymmetric under the interchange of mu and nu indices. So I have 4x4 matrix F mu nu, which is antisymmetric. So the number of independent components is 4 choose 2, which is 6. And that 6 precisely corresponds to 3 components of electric field and 3 components of magnetic field. So electric magnetic fields are now conveniently combined into a single object of F mu nu tensor. It's called field strength tensor, and tensor is just basically a generalization of vector with 2 indices. So F mu nu is a 2x2 matrix, which is antisymmetric, therefore has 6 components, which corresponds to 3 components of E and 3 components of V. So electric field corresponds to the components of F mu nu, where one of the components is the time component 0. And if you multiply by the speed of light, then you can work this out using this original notation of what A should be in terms of scalar potential and vector potential. That turns into this form. And here you get minus sign because here I have F mu nu with derivative upstairs. But I told you that spatial derivative is downstairs. And that's why by converting the upstairs to downstairs, I get a minus sign. And that's how I get negative gradient phi minus vector potential A dot. So that's a notation we used before, but the origin of this minus sign is because of the change from upper index to lower index. So that's something you have to keep paying attention to. But nonetheless, this is the original expression we knew from classical electromagnetism when you write electric field using scalar potential and vector potential. In magnetic field, for example, B1 component turns out to be F23. And again, you need to be mindful of the sign change when you bring the spatial derivative with upstairs the index to downstairs index. And that's why you need to have this minus sign here. So the magnetic field for the X component is indeed written by the curl of the vector potential. And so this now is an explicit way of seeing why this F mu nu field strength tensor really does contain the electric field and magnetic field. And once you know that electric and magnetic fields are written in terms of this 4-vector potential, then you can write this equation, which is very compact. You can see that the mu index is contracted between downstairs and upstairs to make sure that this is a Lorentz invariant contraction of indices. That still leaves one index left over, nu, which is carried over to nu index on the right-hand side of the equation, so that the both sides of the equation transform correctly together. And this is the Maxwell equation. This is just one line. You don't need to write all these different equations now. This is one line equation, which represents the Maxwell equation. And if you work this out, this equation contains, of course, the source for the time component that gives you charge density. That's the first equation among the Maxwell equations. And if you take the spatial components, that gives you this current density. If you work out the left-hand side, that turns out to be this combination of curl B and E dot. So you can write down the first line and fourth line of the Maxwell equations from this single line equation now written in a fully Lorentz invariant fashion. And middle equations, as we talked about before, is just an automatic consequence of the fact that magnetic field and electric field is written in terms of scalar potential and vector potential. But that is also much more transparent in the Lorentz invariant notation, because when you take this combination of derivative acting on the field strength tensor, but contract the indices with this Levi-Civita symbol of the totally antisymmetric tensor, F rho sigma has derivative in it, which is now contracted with this del nu derivative in an antisymmetric combination. So del nu del rho minus del rho del nu vanishes because different derivatives commute. And so this is trivial. So middle two equations, now written in a manifest Lorentz invariant fashion, is obvious because two derivatives commute. So this is just a pure identity. It doesn't represent any field equation or equation of motion. This is just a trivial identity because two derivatives commute, and the name of the identity is called the Bianchi identity. So Maxwell's equation becomes very transparent. It requires only one line equation. We used to write all these four equations simply because we didn't know this Lorentz invariant expression. But once you know this Lorentz invariant expression, the first and last equation just pop out. And second, two equations are just trivial identity due to the fact that two derivatives commute when you take this antisymmetric combination with the Levi-Civita symbol. So now we seem to be making some improvement in a notation. The physics is getting actually simpler by going to relativity, not more difficult, but actually simpler. So that's what we gain by using this notation, using four vectors. Once you put everything into four vectors, you can write down field strength with just one line. You don't need to write down E and B separately. You can write the full Maxwell equation in a single line. And the two middle equations are just pure identities by commuting two derivatives against each other. So that's how you can actually come up with simpler description of physics now that you know relativity. So that's the idea. So every time you make an improvement in understanding, physics is supposed to become simpler And there you go. So you're seeing electromagnetism in a simpler description. And this is how electricity and magnetism got really unified into electromagnetism in a fully Lorentz invariant description. Okay, again, I stop here to see if there are any questions. No?
Yeah,
Go ahead.
so
Go ahead, Andy.
the 2 and 3, or the 1, 2, and 3 will correspond to X, Y, and Z for the bottom magnetic field equation?
Bottom magnetic field equation, you mean just B1?
Yes.
Yeah, so B1 is the X component of the magnetic field, which turns out to correspond to F23 component. And By, or B2, corresponds to minus F31. B3, that's a B component, Z component of the magnetic field, corresponds to minus F12.
Okay, and what is F?
F is this, F mu nu, given by this curl of A with this Lorentz invariant notation.
Okay.
Is that okay?
Thank you. Yeah.
So this F mu nu 6x6 matrix does contain electric field if one of the components is a time component, and contains the magnetic field if both components are the spatial components. And there is no time component because it has to be antisymmetric. That identically vanishes.
Okay.
It's okay? Okay. Dorothea?
Yeah, what's the like?
You're
physical
soft.
meaning
Can you get closer to the
Oh.
microphone?
Sorry. What's the like physical meaning of the electric field having the time component and the magnetic field not? Like, what does that like end up telling us about like E&M or like electromagnetism?
Yeah.
as a
For
whole?
example, so when you choose, for example, I to be, let's say, Y. And if you think about the Lorentz boost along the Z direction, F20 is the electric field, but 0 and 3 mix due to the boost along the Z direction. This is gamma, gamma, beta matrix we looked at before. So as a result, what you find is that when you have electric field along the Y direction, but go to a reference frame that is boosted along the Z direction, you see F23, which is the magnetic field along the X direction. So because the time component, spatial component mixed by this gamma, gamma, beta matrix of the Lorentz transformation, now you can see the electric field along the Y direction from the observer that is moving Z direction appears as a magnetic field in X direction. So the way electric field and magnetic field mix with each other under Lorentz boost is very clear when you use this notation F mu nu. Does that make sense, Dorothea?
Yeah, I think so. That's super interesting. Thanks.
Yeah, so that is generally true. So electric field and magnetic field, again, being a Lorentz tensor, you have to specify your reference frame to talk about what the electric field is and what the magnetic field is. Because when you do a Lorentz boost, they actually start to mix with each other. So what used to be just the electric field might appear to have magnetic field now. And that's exactly the reason why you have spin-orbit coupling in the atom. So when you talked about spin-orbit coupling for the hydrogen atom, that's because electron is moving inside the electric field, Coulomb field from the nucleon. But from the point of view of moving electron, this Coulomb field appears to contain magnetic field, which the spin of the electron feels. And that's how the spin ends up coupling to the motion, in this case, the orbital angular momentum. So that's the origin of spin-orbit coupling. So this is because of this Lorentz transformation, when you go from the rest frame of the nucleus, which has only static electric field, no magnetic field, but because electrons are moving with respect to the Coulomb field, there is a Lorentz transformation going on, and that Lorentz transformation would induce magnetic field out of the electric field, and the spin of electron senses that, and hence spin-orbit coupling. So it boils down to this Lorentz transformation that the whole field strength tensor is a package of electric and magnetic field, they are no longer separable from each other because they transform together into each other under Lorentz transformation. You have to really treat them as a single object. And the spin-orbit coupling in the hydrogen atom is sort of the most familiar example you have seen before of this manifestation that electric field can transform into the magnetic field. Does that answer your question, Dorothea?
Yeah, I was gonna say, so is that like that has some like tell us something about like the induction and like the mixing of
right.
the mixing of like electric and magnetism under time
right.
derivatives. Okay, that's
So
really cool.
so just by knowing the spin-orbit coupling in the hydrogen atom, you are really seeing experimental evidence that electric and magnetic fields turn into each other under Lorentz transformation. To be completely correct, this is a little bit slightly misleading because the electron inside the hydrogen atom is not an inertial frame, it's an accelerated frame. So you have to be a little bit more careful. That turns out to give you extra factor of 2 called Thomas factor. So what I described is sort of correct in the sense that this is an evidence of electric field and magnetic field turning into each other, but actual electron inside the hydrogen atom is not an inertial frame. So you have to do something a little bit more careful. So there is a factor 2 difference because of it. But at least the basic idea that electric and magnetic field is a single object that turns into each other is true in the context of the spin-orbit coupling. So a little caveat, but for the sake of this statement, that is definitely true. Any further questions about this? So you already see there's a lot going on there, and just promoting everything into this fully Lorentz invariant notation is already very useful because you learn new things, how electric field and magnetic field can turn into each other under Lorentz transformation. The only thing you need to know is that these indices, mu and nu, transform by this gamma gamma beta matrix. And when you're doing Lorentz boost along the z direction I talked about, then x and y components unchanged. That's why if you look at the EY, I don't need to touch y component, but 0 gets touched by the Lorentz boost, and 0 turns into 3 or z direction with this gamma gamma beta matrix. And that's how I know that that would give you B1, namely magnetic field in x direction. So electric field along the y direction boosted in z direction turns into the magnetic field along the x direction. So that's something you can tell right away by knowing this notation, F mu nu. Just knowing the electric and magnetic fields is part of F mu nu already tells you how electric field and magnetic field would turn into each other under Lorentz transformation. Okay, I'm just keep repeating myself, but it's kind of important point, so it's probably worth it. Any other questions on this slide? Everything okay? And again, we can always come back and talk more about this. Okay, and the gauge invariance also becomes a lot simpler. So we talked about this fact before. The field strength of the electromagnetism is all you care about in classical mechanics, because all you care about is solving the equation of motion, and the equation of motion involves only the field strength, not scalar potential or vector potential. And we just learned that field strength is written in this way in a manifestly Lorentz covariant fashion. And then we also think about gauge invariance. So we figured, given how electric field and magnetic field are written using scalar potential and vector potential, we found this ambiguity in scalar potential and vector potential. Even if you change scalar potential by some time derivative of arbitrary function chi, and change also vector potential at the same time by the gradient of the same function chi, you can see this difference due to chi, scalar function, just cancels between these factors so that the electric and magnetic fields don't change. And that is the gauge invariance we talked about before. And now using this Lorentz invariant notation, gauge invariant looks also very simple, which is just to change A mu as a whole, which contains both scalar potential and vector potential in it, to another vector potential that differs by this fourth derivative acting on the scalar function chi. So again, I don't need to write separate transformations for scalar potential and vector potential. Now they are unified into this 4-vector A. And the gauge transformation is again just single line thing, A mu changing to A mu prime by this 4th derivative of function chi. And if you write it this way, the fact that field strength is gauge invariant is also very simple, because it's just that you're changing A mu by del mu chi, and I'm putting del nu chi in here. This gives you del mu chi. I put del mu chi in here. That gives me del mu chi. Del mu and del mu are derivatives in different directions, so they commute. And as a result, F mu doesn't change. So that's it. So in the previous notation of separating scalar potential and vector potential, we need to find this cancellation by carefully choosing time derivative and the spatial derivative. But now that they're unified into this single line thing, then checking gauge invariance of the field strength is also a single line thing, and it's very obvious. So again, that's another improvement that relativity makes our life easier. So it's easy to tell that under gauge transformation, which is very simple, just given by this 4th derivative, the field strength tensor doesn't change. Therefore, the Maxwell's equations don't change. They depend only on the field strength. And electromagnetism is gauge invariant. That's a statement we checked before by grinding through this vector calculus. But once again, things become a lot easier and more obvious once you use this Lorentz invariant notation. So, you might complain, why didn't you learn it this way from the very beginning? And everything was a lot easier. Well, this is the idea in pedagogy, that you start with things you're familiar with, and you start to build up, and you go step by step. And so that's how you came to this Lorentz invariant Maxwell's equation now. Now you build it up so that this becomes much more obvious. But if you were born in the world where speed of light is like a 30 miles an hour, in that world, your daily experience already involved relativity. You experience just by going on jogging, your watch gets slowed down compared to the grandfather's clock in your home, right? So if you were born in that kind of world, you grow up with relativity, then it would have been probably a lot easier to study electromagnetism, because then you can jump into this notation right from the beginning. Unfortunately, we are not born in that world, so we have to build up from Newtonian mechanics first, Maxwell's equations next, and then relativistic equations later on. So that's the steps you have followed, but that's the way things are. Just in case that you haven't heard of this, that George Gamow is the famous physicist who did a lot of interesting things in nuclear physics, cosmology, quantum mechanics, and all that thing. And he has written a popular science book called The Adventures of Mr. Tompkins. And Mr. Tompkins is a banker. And on a holiday, he was single, and he had plenty of time to kill. And he looked at the newspaper and found that there was some public lecture on relativity. So he decided to go and check that out. But the professor started talking this monotone and writing a bunch of equations on the board. And eventually Mr. Tompkins started to nod and fall asleep. And he dreams actually about relativity. And in his dream, he lives in this world where speed of light is like 20 miles an hour. And he pedals on a bicycle, and he sees all the shops start to shrink due to Lorentz contraction. And when he gets off the bike, then his watch shows different time from the clock tower. So he starts to experience these relativistic things in his dream. So that's the kind of world I had in mind when I mentioned that if you grow up in that kind of world, relativity is natural to you, and this would be the notation you would use from probably elementary school, but we are not living in that world. So I really recommend that book. It's really fascinating. The book also talks about the world where H bar is bigger. So when you go to pool and strikes a billiard ball, it starts to spread out on the entire pool because of uncertainty principle. And that's something you experience also firsthand when you grow up in that kind of world. So that sounds like a lot like a book, Einstein Dreams. I don't know this book, Einstein Dreams. Is that good?
Yeah, it's very, very good. It's really short, but it's my favorite book. It's like really similar, actually. It's like different like short stories, sort of, or like, yeah, of like worlds where different things about relativity are exaggerated. So there's like one where there's like a class structure that like people who have like the like upper class like lives in like really high buildings because they're like further away from gravity, and it like slows down time. It's it's really good. It's like really beautifully written.
Okay, I check that out. And George Gammoff's book, I think, went out of print at some point, and the original version was a bit sexist. So people rewrote the book with a more modern version of it. So I believe that version is still on sale. So anyway, so everything becomes simpler about electromagnetism once you know relativity. So that's the main message here. But now comes a problem. So now we have this Lagrangian we used when we talked about, for example, superconductivity of the Cooper pair field psi with charge 2e. We made sure it was gauge invariant. And here is the Lagrangian for the electromagnetism. And now that we know the relativistic notation, and epsilon mu is 1 over c squared, right? So I can also promote this Lagrangian to a fully relativistic expression, which is just f mu nu, f mu nu. And once again, I need to make sure that I contract indices between upstairs and downstairs to be consistent with the relativistic invariance. We know what f mu nu is. And if you bring mu and nu downstairs, it changes the sign of the spatial component. As a result, this f mu nu turns into e squared minus c squared b squared. So the full Maxwell's Lagrangian is just single term f mu nu. And this is a point Dorothea liked before when I mentioned this. Once you know relativity and know that a mu is a 4 vector, the only gauge invariant objects you can write is f mu nu. And out of f mu nu, only Lorenz invariant you can write down is f mu nu, which tells you that Lagrangian for the electromagnetism is e squared minus b squared. You were forced to use e squared minus b squared because that's the only thing you can write down consistent with the Lorenz invariance. You could write down higher order terms like f mu nu squared and stuff like this. But at the lowest order in a field strength, then this is the only thing you can write down, which turns out to be the correct Lagrangian for the electromagnetism, which has to be the case because Mother Nature knew she was Lorenz invariant. So she invented all this relativity stuff. And then f mu nu is the only thing we could use consistent with the Lorenz invariance and gauge invariance. F mu nu is the only Lorenz invariant you can construct out of it. And therefore, the action had to be e squared minus b squared, no other choice. You can derive this Maxwell's Lagrangian from first principle. We used it because we knew this was the right Lagrangian, but we now know why this is the right Lagrangian. And that's all enforced on us by the Lorenz invariance of the space-time. So that's great. Now we seem to understand everything about the second line. But what about the first line? And then we have a problem. The first line describes non-relativistic particle. We quantized this many times already before, Schrödinger field theory. If we found energy is p squared over 2m, that's clearly the sign that we are dealing with something non-relativistic. So the second line is great. All relativistic, gauge invariant. But the first line sucks now. We loved it before, but now we are faced with this problem. We have to now also promote the first line into a Lorenz invariant theory. So we need to make the matter field also Lorentz invariant. Maxwell part is Lorentz invariant from right on the get-go. But the first slide for the matter field is not. So now we need to try to come up with Lorentz invariant theory for the matter fields. And the first thing we're going to try is the Klein-Gordon theory I mentioned earlier. So matter part is not Lorentz invariant, so we need to change it. So that's the motivation of now trying to move into fully Lorentz invariant quantum field theory. Okay, any questions about this? And Dorothea, this is what you're looking for. I hope you like this. Hello? Maybe she's not there. Okay. All right, any other questions?
No, I'm here. Sorry, this is really cool. Thank you.
All right, good, good. Any other comments or questions? All right, let me move on. So now we have to come up with the Lagrangian for the matter particle, and we make an educated guess, trying to come up with it. So what we learned from non-relativistic Schrödinger equation is that energy is p squared 2m. This is definitely non-relativistic. We have to change that. But we learned two more things, that energy has to do with IH bar del T, and momentum has to do with H bar over I gradient. And we learned about the sign difference too. So the reason why energy has I, but momentum 1 over I, had to do with the fact that going from energy momentum 4 vector to derivative 4 vector, derivative 4 vector is derivative index downstairs, energy momentum 4 vector has index upstairs. I need to change the sign of spatial components, and that's the origin of 1 over I instead of I. So that's something we have learned already a couple of slides ago. So we now get this idea to be consistent with the relativity, that energy is described by time derivative, spatial momentum is described by the spatial derivative. So this part looks relativistic, but E equal p squared over 2m is not. So now we know what we should do to come up with an educated guess of the field theory equation. So we preserve this piece, E is del T, P is gradient. We stick to this, but we change E equal p squared over 2m. And non-relativity Schrödinger equation combine all of these three ingredients and come up with this equation. So we follow the same path. So E equal p squared 2m turned into this equation because I replaced E by time derivative, P by spatial derivative. That's how you came up with the Schrödinger equation. But what we need to change now is this E equal p squared minus 2m to a relativistic expression. So the Klein-Gordon equation uses this one instead. That's a relativistic equation. We also derived from first principle. So this, if you move this p squared c squared to the other side of the equation, the left-hand side is p mu with indices contracted with upper and lower indices. And that turns into Lorentz invariant, namely m squared c to the fourth. I just moved p squared c squared to the other side of the equation. So this is now the right expression for the relativistic energy. So instead of using this E equal p squared 2m to write down the Schrödinger equation, now I use this relativistic expression for energy and momentum, but then do the same replacement that energy is time derivative, momentum is a spatial derivative, and there you go, this is the equation. And if I move this p squared piece to the other side of the equation, then I find this combination of del T squared minus spatial derivative squared. That's something we learned as the Lambertian. And dividing both sides by h bar squared c squared, this piece here turns into m squared c squared by h bar squared. Now I have an equation for a massive matter field of mass m with fully Lorentz invariant expression. And this is the educated guess. And this equation is called Klein-Gordon equation, according to the names of people who came up with Mr. Klein and Mr. Gordon. And it's actually an interesting story. Apparently, it was Schrödinger who came with this equation first. And Schrödinger being Schrödinger, he was strong enough to apply this equation right away to the hydrogen atom and worked out the energy levels of the hydrogen atom using Klein-Gordon equation, and then realized that the relativistic correction came out wrong. And it turns out the Klein-Gordon equation describes spin-less particle, spin-zero particle. It doesn't have a spin. Therefore, it doesn't have the spin-orbit coupling. Therefore, it doesn't give you the correct energy spectrum for the actual hydrogen atom. So he got stuck. Something is wrong with this equation. And then he decided to cheat. Okay, this equation seems to give me more or less right energy spectrum for the hydrogen atom, but it's wrong at the level of the relativistic correction. So instead of writing down this fully relativistic equation, if I cheat and go to a non-relativistic equation, at least within that non-relativistic approximation, the answer is right, because I dropped the relativistic correction. So that's apparently what he did. He first wrote down relativistic equation, which gave him wrong answers, but because how much wrong that is only in the relativistic corrections, then he was guaranteed once you take a non-relativistic approximation, it was correct within that approximation, and hence the Schrödinger equation. Apparently, that was the history of the Schrödinger equation. So quoting the Klein-Gordon equation is actually not quite right. But if you call the Schrödinger equation to this one, then that will be maximally confusing. So, we basically decided that we give credit to the second set of people who came up with this equation of Schrödinger, because we'd rather refer to this equation at the non-relativistic level as the Schrödinger equation, and the name stuck. So that's the story. But anyway, so by following the same argument that goes to the Schrödinger equation, by replacing energy by time derivative and momentum by spatial derivative, I can promote this relativistic relationship between the energy and momentum to a full-blown Lorentz invariant field equation called Klein-Gordon equation. So now that we have Lorentz invariant field equation, we try to come up with a Lagrangian that reproduces this field equation. And the minute you have a Lagrangian, you can go through the same steps we have gone through of the canonical quantization, like what we did for the Schrödinger field. And once you go through it, then field equation turns into creation annihilation operators. Then you can build a Hilbert space and see what kind of Hilbert space you get. And that's a process we'll go through. But I hope the argument is very clear. So instead of using this non-relativistic relationship between energy and momentum, we use this fully Lorentz invariant relationship between energy and momentum we derived a few slides ago. This is just the Lorentz invariant product of P mu by contracting lower and upper indices, right? And once you have this fully Lorentz invariant expression between energy and momentum, I go to the same replacement of energy by time derivative, momentum by the spatial derivative, and then that would give us this equation, which manifestly does look Lorentz invariant because it's written in terms of this D'Alembert with 4 corners for 4 space-time dimensions. And so hence, this is the candidate equation we'd like to start with. And then using this candidate equation, we come up with a Lagrangian. We go through canonical quantization. We do the mode expansion to come up with the creation annihilation operator, and then build a Hilbert space out of it. And we see what we get from that Lagrangian. So that's the steps we're going to follow. So I hope it's clear where we are trying to go from here. But anyway, so let me pause here again to see if there are any questions. Again, don't be shy. Everything clear? Okay, so then now that we have this field equation, we try to come up with a Lagrangian whose Euler-Lagrange equation is this Klein-Gordon equation. Cameron's video turned on. Do you have a question?
No, I don't.
Oh, okay.
I just saw it turn my camera.
Good. All right. So we try to come up with the Lagrangian whose Euler-Lagrange equation is indeed this Klein-Gordon equation. And that actually is very simple. So we got a field equation. Oh yeah. The one thing I had to actually say before getting into Lagrangian. So there is actually one major difference between the Schrödinger equation and Klein-Gordon equation. Schrödinger equation is the first order differential equation in time, because it has to do with E, not E squared. So this is the first order differential equation in time. And if you remember what you studied in quantum mechanics class, it was crucial that the Schrödinger equation was the first order equation in time to make sure that this psi can be interpreted as the probability wave with a conserved probability. But Klein-Gordon equation is second order equation in time. So it turns out phi cannot be interpreted as a probability wave. And so that's the point I wanted to make on this slide. So let's see how that goes. So Klein-Gordon equation is a second order differential equation in time. And when you build phi star phi, like what you did for the Schrödinger equation, psi star psi for the Schrödinger wave function represented the probability density, because the spatial integral of psi star psi was just a normalization of the wave function. It doesn't change with time. Therefore, you could choose the normalized wave function, and then it never changed. The psi star psi doesn't change as a function of time, and that was because the Schrödinger equation was the first order differential equation in time. But now Klein-Gordon equation is a second order equation in time derivative. And second order differential equation is sort of like the usual equation of motion for point particle. F equal ma is a second order differential equation, right? F is the force, and a is x double dot, second time derivative of the position. And because the equation of motion is second order differential equation, we have to specify two initial conditions, namely initial position and initial velocity. The same deal here, because Klein-Gordon equation is a second order equation in time, we have to specify two independent initial conditions, namely phi itself and also phi dot. They are independent initial conditions. What that means is that even if you specify phi star phi as initial condition, that's not sufficient. And time derivative of phi star phi involves phi dot, which is independent from phi star phi. Therefore, phi star phi doesn't guarantee the probability is conserved. And in fact, the only conserved full current I can come up with, consistent with the Klein-Gordon equation, is this one, which ends up being actually useful as the charge density of this massive particle phi. But this charge density, having this derivative and a minus sign in between, this is conserved, but it's not positive definite. So it doesn't qualify as a probability density. So it's conserved, that's good, but it's not positive definite. So it doesn't qualify as the probability density. For charge density, it's okay, but for probability density, it's not. Phi star phi instead is positive definite, but it's not conserved. So I cannot satisfy two requirements at the same time. If we want to have the probability interpretation of the wave equation, you need to come up with positive definite density, which is also conserved. What we see here with the Klein-Gordon equation is that I can come up with something that's positive definite, like phi star phi, but it's not conserved because its time derivative is independent. I can come up with something conserved, but its density is not positive definite. I cannot satisfy two requirements at the same time. So Klein-Gordon equation, when Klein-Gordon came up with at the first time, was actually abandoned because it doesn't seem to conform to that idea of the quantum mechanics being described by a probability wave. But then there was a second coming of the Klein-Gordon equation. After a while, Heisenberg and Pauli realized, well, look, the probability wave is just for the purpose of single particle quantum mechanics according to Schrödinger. But if you go to multi-body mechanics, you have to make it multi-body wave function. So that was not the right thing anyway. And now we know we have to go to quantum field theory rather. So even though Klein-Gordon equation was not eligible as an equation for the probability wave, as far as the quantum field theory is concerned, Klein-Gordon field is definitely eligible for a quantum field theory, because quantum field theory has a different way of deriving probability wave. Phi is not the probability wave. Schrödinger field is not the probability wave. It's the quantized fields, and quantized field is actually creation-relation operator, and you define states by acting the field on the vacuum state, and the coefficient function had the interpretation of the probability wave. So we don't need to regard phi to be the probability wave anymore, but rather we regard phi to be a quantum field. And as long as phi ends up being creation-relation operator, not the probability wave, this requirement of satisfying positive definite conserved density is no longer necessary, and we could use it now. So that's the second coming of the Klein-Gordon field by Heisenberg and Pauli, and that's how we can use this relativistic field equation now in a different context. So history of physics is often very confusing and interesting. The people invent something. Schrödinger invented Klein-Gordon equation, but he abandoned it because it didn't work with the hydrogen atom and came up with the Schrödinger equation. Then later on, people realized, that's Max Born, what Schrödinger equation describes is a probability wave. But in order to use Klein-Gordon equation as a relativistic version of the Schrödinger equation, it was not eligible because it didn't lead to the conserved probability, and it was discarded. So it was discarded twice, and then got resurrected by Heisenberg and Pauli as the quantum field theory field equation, not the probability wave. Then all of a sudden, we can use this relativistic equation once again, and that's exactly what we end up doing. So I hope this argument is clear. So even though the Klein-Gordon equation was there from early on in the history of quantum mechanics, it could not be used when people were trying to stick to this idea that wave equation has to do with probability wave. But that shackle, we got released from it when we decided that phi is a quantum field instead, not the probability wave. Then all of a sudden becomes a great candidate for quantum field theory because it's manifestly Lorentz invariant. So let's just go ahead and try to see what you can get by quantizing this field. And that's the next slide, I believe. Okay, let me pause here again to see if there are any questions about this argument. Excuse me. Andy, you were trying to ask a question? You're muted. No? Okay. Anybody else? Okay, then let me move on. So now we have this second or third coming of Klein-Gordon equation. So we cannot regard it as a relativistic version of Schrödinger equation because it doesn't have the interpretation of the probability wave. There is no positive definite conserved probability consistent with the Klein-Gordon equation. So it doesn't work. But instead, we regard Klein-Gordon equation as an Euler-Lagrange equation of a field, which we would like to quantize in a similar way that we quantize the Schrödinger field. So in Schrödinger field theory, Schrödinger field was not probability wave. It was a creation-addition operator instead. So we try to stick with the same idea. Then what is a Lagrangian that would reduce the Klein-Gordon equation as its Euler-Lagrange equation? And can we quantize it? So that's the next set of questions we need to ask. And I don't think there are any questions about this slide. So let me jump right into it. So the Lagrangian of Klein-Gordon field is given by this. Here I'm assuming phi is a complex field, similar to Schrödinger field. And del mu phi, as I said, is the derivative 4 vector, which is naturally downstairs. But once you have this del mu phi, which has this index mu, you can immediately build a Lorenz invariant by putting it together with the derivative upstairs by flipping the signs of the spatial components. Then this del mu phi star del mu phi is Lorenz invariant. And so that qualifies as the integrand of the Lagrangian. At the end of the day, you write action, which is the time integral of the Lagrangian. Then time integral of the Lagrangian now has time integral and 3 spatial integrals. So that's a full integral of a spatial 4-dimensional space-time. That by itself is Lorenz invariant. And del mu phi star del mu phi is also Lorenz invariant. Then the action as a whole is Lorenz invariant, and that's what we want. So this now qualifies as a term in the Lagrangian density. And another term that qualifies is just phi star phi, that's sort of similar to chemical potential we had for the Schrödinger field. And together with this constant coefficient, which we choose to be m squared c squared by h bar squared, such that this reproduces the Klein-Gordon equation. And that check is very easy. First of all, action, time integral of the Lagrangian is manifestly Lorenz invariant. I already said that because space-time integral, which includes both space and time, is Lorenz invariant. And this del mu phi star del mu phi has indices contracted between lower and upper indices. That's Lorenz invariant. Here, you don't have any indices. That's Lorenz invariant from the beginning. And then you can derive the Lagrange equation very easily by taking the small variation of phi, by taking variation of phi star and acting this derivative on the other side by doing integration by parts. I have del mu with minus sign from integration by parts. That's a D'Alembert with minus sign. Variation with respect to phi star gives you m squared c squared by h bar squared times phi with a minus sign. I remove minus signs both from both terms, and that's nothing but the Klein-Gordon equation I had on a previous slide. So it's easy to see that this Lagrangian does lead to the Euler-Lagrange equation, which is nothing but the Klein-Gordon equation. So now we have an action or Lagrangian, which is consistent with the special relativity, which is consistent with the Klein-Gordon equation. But now that we have the action, we know how to identify the canonical momentum conjugate to phi variable, then set up the canonical commutation relation, and then quantize it to find the mode expansion in terms of creation-addition operator. And that's exactly what Heisenberg and Pauli did. And that leads to a consistent quantum field theory. So phi was dead for the probability wave, but now all of a sudden came back as a very good field equation that gives you the Lorenz invariant quantum field theory. So now that I'm running out of time, let me just flash it, how that goes, and then come back and talk about this in more slowly on Friday. So I now have the Lagrangian, and from this Lagrangian, I can identify the canonical momentum. So by writing out this mu contraction, time component is 1 over c del t. squared, that's 1 over c squared phi dot phi dot. Spatial component, I have to reverse the sign when I interchange the lower and upper indices. So there's a minus sign with spatial derivatives, again contracted over x, y, and z. And this term is just the same as the first line. And looking at this expression, I can identify phi dot. So by taking phi dot derivative, I can identify the canonically conjugate momentum, which is 1 over c squared phi dot star. So then I know what the correct canonical commutation relation is, which we already used many times for the Schrödinger field. I'm just applying the same idea. So here's the canonical commutation relation between phi and phi star dot. And it turns out that that is consistent with the creation annihilation operator, which is now given in terms of this mode expansion of the field operator phi. Some complicated normalization factor, but let's not worry about it for now. And here's the annihilation operator A and creation operator B dagger. And this is not A dagger because we assume the phi is a complex field, not necessarily Hermitian. So this part and that part are independent from each other. And similar mode expansion also for phi dot. So it turns out that this complex Klein-Gordon field now contains 2 sets of the creation annihilation operators. A and A dagger satisfy the commutation relation or creation annihilation operator, but B and its conjugate B dagger also satisfies yet another set of creation annihilation operator. So this is the quantization of Klein-Gordon field. So I made sure that Lagrangian leads to Klein-Gordon equation. It is Lorentz invariant. So far, so good. Then I identify the canonically conjugate momenta. By writing down this canonical commutation relation, I came up with a consistent mode expansion in terms of creation annihilation operators. But odd thing I discovered now is that I seem to have 2 independent sets of creation annihilation operators. That turns out to be the beginning of the discussion of antimatter. It turns out that A and A dagger describes matter particle, but B and B dagger describes antimatter particle, which is now a new theme that comes together when you actually put the Lorentz invariance together with quantum field theory. So that's what we would like to talk about on Friday. So as I said, we know how to come up with the Lagrangian that reproduces Klein-Gordon field. Once we have the Lagrangian, we go through the similar familiar procedure of canonically quantizing the field, and out comes the creation annihilation operators. And we seem to have discovered something new, namely that in addition to matter particle we wanted to come up with, we also came across with the antimatter particle. So we will see that in more detail on Friday. Okay, so that's it for today. Any questions?
I have a question.
Go ahead, Cameron.
So yesterday or last time we met, we were talking about like just going over the decay rate. And so I was asking about that one complex term that was like non-Hermitian. I was like kind of like looking into it a little more. Like, would that represent something like an unstable state where you're considering like a transition between 2 energy states? So like basically that complex term for like what you describe with the energy would be some type of correlation factor.
Yeah, so the imagination part of energy gives you the decay, yes.
Okay.
Is that connected with what we just talked about, or is it totally independent question?
Oh, no, it's just that I think you mentioned you were going to put up like a tunneling like problem like on B courses. And
oh, yeah. So I haven't done that yet. Yeah, so I would do that. And so that's where you can solve the Schrödinger equation, non-relativistic Schrödinger equation, and find complex eigenvalue of the Hamiltonian. So I will post that note. Sorry, I forgot to do that. Thank you.
No, don't worry about it.
Anything else? Okay, so I see you on Friday.
Thanks.
Stay safe.
Thanks, bye.
Professor, I have a quick question.
Oh, go ahead.
So correct me if I'm wrong, but we used to write our mode expansions in terms of like momentum and then like the operator of the negative momentum. And so
Mhm.
why doesn't that apply here, I guess?
Let's see. No, we are doing the same thing here. So showing the same slide. So here I have IP dot X. That's the positive momentum P, but this piece has minus I in it.
Oh, okay. Gotcha.
And if I were Hermitian, then this second term will be Hermitian conjugate of the first one. So B dagger will be the same thing as A dagger. But we
Okay.
assumed phi was complex, and that's why A and B are now independent from each other. But we are applying exactly the same idea of writing a mode expansion in terms of positive and negative exponents.
Okay, that makes sense. Thank you.
Okay, good. Thanks for the question. Got anything else? Can I finish? Okay,
Two
Earl?
quick ones.
Okay.
One about the homework, which was that
Huh?
when you said when you say that protons are accelerated to an energy of 7 GeV,
Mhm,
is that in
mhm.
reference to the momentum?
I'm sorry?
When the problem says that protons are accelerated to the energy of 7 GeV,
Uh-huh.
is that in reference to the momentum?
No, 7 GeV is the energy.
The energy. Okay.
Yeah, even though it doesn't really matter because it's so high. No, so 7 TeV, 7 TeV, right? Did the homework
7
problem
G.
says TeV? Okay, good.
And a small clarification about something over within your slides about the Bianchi identity. I didn't catch that as to what that was trying to show.
Oh,
up
it
as.
says 7 GeV. That's a mistake. So I need to correct that. Well, thank you. Okay, sorry. So Bianchi identity, back to Bianchi identity. Yes, can you ask the question again? I was distracted.
No worries. What I wasn't able to catch what precisely the Bianchi identity was. It
Here we
seemed to
go.
be some derivative.
So Bianchi identity is referring to this equation at the bottom. Epsilon mu nu rho sigma, del nu f rho sigma vanishes.
Okay. And what does that epsilon in reference to? That since it has 4 different subscripts, that doesn't look like the Levi-Civita symbol at all.
So the Levi-Civita symbol in 4-dimensional space-time. So all of these indices take values from 0 to 3. And that's why you have 4 indices to make them totally antisymmetric from 0, 1, 2, 3.
Got it. So 4-dimensional Levi-Civita symbol applying to the derivatives. Okay. Thank you very much.
Is that good? Okay. All right. And I see something in the chat window. Thanks, Professor. Okay, good. All right. Then I'll see you on Friday.
See you on Friday.
Bye.